All right, so we had one more part in this example that we needed to work through, and it was asking when the particle was slowing down. The idea of slowing down or speeding up is concerning acceleration. So we need a function for acceleration before we can start to answer this question. Let's see, where did we get? Oh, here we go. We found our velocity function here. And we had it in this form, but also in factored form. What we want to do is take the derivative of this, because the derivative of your velocity function will be your acceleration function. So we want the derivative of 81 minus 9t. What I'm going to do, since I ran out of space on this page, and I'm going to get another page here. So there's my v of t up there. My acceleration function, a of t, this is for part D. My acceleration function is going to be equal to v prime of t. And what's going to help me is if I factor a 9 out of the numerator here. So I can write that this way. d dt of 9 times, this would look like 9 minus t squared up here, over t squared plus 9 quantity squared. The reason I wanted to factor that 9 out is because now this is a constant times a function of t, and from the beginning of chapter 3 we know that there's a constant multiple rule. All I really need to do is leave that 9 where it is and just take the derivative of this function using the quotient rule. So quotient rule says take the bottom function times the derivative of the top, so that's going to look like t squared plus 9 quantity squared times the derivative of my numerator, which is negative 2t. I don't want to forget that I have a 9 out there. And then I subtract the top minus the derivative of the bottom. So 9 minus t squared. The derivative of the bottom is going to require the chain rule, so that's going to look like times 2 t squared plus 9 to the first power, so I'm treating that like it's the power rule. Multiply that by the derivative of the inside, which is going to be 2t. Okay, all over this guy squared. So if I square something that's already being squared, that's the same as taking it to the fourth power. I'm going to have t squared plus 9 to the fourth. That denominator is not really going to matter for what we're doing with this function here. This is really messy. I'm going to try to simplify this as much as possible. One thing I notice is this is really just made up of two large terms here, and both of them have a t squared plus 9 in common, t squared plus 9, and they also have a negative 2t in common. This 2t times this minus here, if I think of that as a negative 1 times all of this stuff, I can bring that negative 1 over here and call that a negative 2t. So what I'm going to do is factor a negative 2t times the quantity t squared plus 9 out of that numerator. Negative 2t times the 9 that's already there is going to make that negative 18t. Here's the t squared plus 9 that I pulled out, and now we need to look at what's left. So I pulled out the negative 2t, a t squared plus 9, but this was squared, so there's still a t squared plus 9 left over there. This negative came out, so now I'm looking at a plus here. This 2t came out, the t squared plus 9 came out, so now I'm just left with 2 times this guy. Let's go ahead and multiply the 2 in there. 2 times 9 would be 18. 2 times negative t squared is minus 2t squared. Okay. All over t squared plus 9. This simplifies down even further, so I have negative 18t times t squared plus 9 times 9 plus 18 is 27. T squared minus 2t squared is negative t squared, so I have 27 minus t squared over, that should be to the fourth power there, t squared plus 9 to the fourth. And then almost there, this looks kind of like a difference of squares. And even though 27 is not exactly a perfect square, I can still factor it using the same technique. So I have negative 18t times t squared plus 9. This would look like root 27 minus t, root 27 plus t, okay? And yeah, I can simplify that square root of 27 to 3 root 3, but I don't really care so much about that. This is how this is going to factor. Now, Before I go any further, let's talk about what it would look like for this particle to be slowing down. It's not a simple matter of the acceleration function just being positive or just being negative. You actually have to think about what the velocity looks like as well. And here's the reason why. Let's suppose way down here I have a graph of a velocity function with respect to time. Okay? In order for this particle to be slowing down, that means that the velocity needs to be getting smaller in the sense that it's getting closer to 0, because 0 would mean that we're at rest. That's as slow as you can get. So there's two ways that your velocity function can approach 0. Your velocity can be positive but decreasing. Notice that if this is part of my graph of my velocity function, I would be slowing down because I'm starting with a large positive velocity and moving towards a smaller positive velocity, so it's kind of going in the direction of 0. But another way you can have your particle slowing down is if your velocity is negative but increasing. And the reason for that, it seems like an increasing velocity would mean that you're speeding up. But if your velocity is negative to begin with, remember that means you're traveling at the absolute value of that velocity, but to the left. And if that velocity is increasing in the sense that it's getting closer to 0 from this side, then that increasing velocity actually means that you're going closer and closer to being at rest. So this would also technically be slowing down. In this case, we have a positive velocity, so I'm going to say v is greater than 0, but a negative acceleration. And the reason I know the acceleration would be negative in this case is because, again, the acceleration is the derivative of the velocity, which means it would look like it would represent the slope of tangent lines to this graph. So if this graph is going downhill, all of the tangent lines will have negative slope. So again, one way your particle can be slowing down is if you have a positive velocity and simultaneously have a negative acceleration. Alternatively, if your velocity is negative, but your acceleration is positive, which would be this case. Again, my velocity is, the graph of velocity is below this t-axis, making it negative, but it's traveling uphill to move towards 0. So the acceleration would be positive because the slopes of all these tangent lines would be positive. So these are the two cases in which our particle can be slowing down. And notice one way of summarizing both of these cases in one is to say that this particle is slowing down only when your velocity and your acceleration have opposite signs. One is positive while the other one is negative. So now coming back up here, if I want to determine where my acceleration function is positive or negative, I first need to find the zeros of that function. Okay. Now again, this looks really, really messy, but it's okay because analyzing is not as hard as it might look. So the numerator is the only thing that can turn this thing into a 0. The denominator is not going to play a role in that. So this will only equal 0 if my numerator equals 0. Now I've already factored my numerator, and notice if t equals 0 or plus or minus root 27, that is where the zeros of this numerator would come from. And I can even scrap one of those. The negative root 27 we can get rid of because, again, we think of time as being positive. We don't think of it as being negative. And so a negative root 27 for t kind of doesn't make sense in this context. So that means, I'm going to say, implies that t equals 0 or positive root 27. And again, I don't care about simplifying that radical. It's not going to really do anything for me. One thing that will help, though, is to kind of know roughly what this is equal to as a decimal. So you could plug root 27 into a calculator, for example. It's roughly 5.196. And I'm going to show you why that's important here. So if I were to put those zeros in a number line, kind of like I did with my velocity function, and I'm actually going to reuse that number line that I did in the previous video. 0 would be here. I'm going to put root 27 somewhere around here. And now what I want to do is determine where my acceleration function is positive, where it is negative. This gives me two intervals to worry about, 0 to root 27 and root 27 to infinity. Think of test points in there. Remember, root 27 is approximately 5.196. So you can use that to sort of help determine what test points you should be using. So from 0 to root 27, let's try plugging in a 1, for example. Okay, so I have negative 18 times 1. This factor is going to be negative. Notice that t squared plus 9, no matter what I plug in for t, will always be positive. So I don't even really need to think about that one. Root 27 is greater than 1. So root 27 minus 1 would be positive. I have a negative times a positive times a positive. So far the whole thing works out to negative. And then root 27 plus 1 is also positive. Negative times positive would be negative. So my acceleration here is negative. It's less than 0. I could do a similar analysis, pick a test point that's bigger than root 27, say 10 or something. You'll find that the acceleration is positive there. You can verify that doing something similar to what we just did. Now, over here, up here, I did something similar with my velocity function. So I'm going to copy that here. Okay. And the relevant points there were 0 and 3. Now I want this to sort of overlap with my acceleration. So 3 would be to the left of 5.196. I'm going to put 3 just around here. This part doesn't need to be perfect. I just need to make sure that no number is to the right or to the left of something that it shouldn't be. Previously we determined that velocity was positive from 0 to 3 and negative from 3 to infinity. So again, what are we looking for? I need to determine points at which the velocity and acceleration have different signs, because that's going to be where we are slowing down. Okay, so essentially I have 3 subintervals to look at. The interval from 0 to 3, which is this, from 3 to root 27, this guy, and then from root 27 to infinity, because that's where these graphs sort of overlap. Starting from 0 to 3, I have positive velocity here and negative acceleration. So the signs are different there. That means that on the interval from 0 to 3, our particle is slowing down. Then from 3 to root 27, what happens there? Well, velocity is negative after t equals 3, so for everything greater than 3. Acceleration is still positive in that interval as well. So positive and positive means I don't have different signs. We are not slowing down in that interval. That would actually suggest that we're speeding up. And then as I go from root 27 to infinity, velocity is negative there, but acceleration is positive there. So that's another time when the particle would be slowing down. Okay? So again, it's important to note that for a problem like this, it's tempting to just think, we're slowing down when our acceleration is negative. But there is more to it than that. It depends on what's happening with your velocity as well. So there's a little bit more depth to a problem like that. Let's go ahead and move on. Snag this page here. So far, the only application that we've looked at in this section has been what your book's going to refer to as just the physics problem for this section, the position, velocity, acceleration stuff. But we want to look at other applications that we haven't really investigated yet. So the next one is going to fall under the category of biology, and specifically ecology. We're going to look at population growth. So a population can include any type of living organism capable of reproducing. That way the population can change over time. So it can be people, it can be animals of some kind, it could be plants, it could be bacteria. It's anything that is a living organism capable of reproduction. So let's define a function, n equals f of t, and this function is going to represent the number of individuals in a particular population of organisms at time t, whatever t is measured in. Now, when we study the growth or decline of a population of some kind of organism, we're interested in knowing the rate at which the population is growing or shrinking. So the rate of increase or decrease. And we're going to look at this in more depth in the next section, but we can start looking at it here. Okay, so in order to start looking at what that rate would look like in context, suppose that time progresses from t equals 1 or t1 to t2. So these are 2 times we increase from t1 to t2. then we might see a change in our population as that time passes. And we would denote that as delta n equals f of t1 minus f of t, f of t2 minus f of t1. The population at time t2 minus the population at time t1 is a measure of how many individuals we gained or lost over that time period. It follows then that the average rate of change in that population over the time interval from t1 to t2 would look like this: delta n over delta t, or f of t2 minus f of t1, this quantity, minus t2 minus t1, or over t2 minus t1. That would be the change in time. Okay? As you would expect, when we see a rate like this, an average rate of change, we want to look at it as an instantaneous rate of change, which would require us to apply a limit to it, specifically the limit as delta t goes to 0. Now, from what we've worked on so far, we know that that will lead us to a derivative. So that would suggest that the derivative of our function, our population function, f of t, gives us the rate of growth in that population, growth or decline. There's a fundamental problem, though, in thinking of this type of function in this way. By the way that we've defined this function, it's discrete. And what that means is that it can never take on non-integer values. F of t can only ever equal whole numbers because you can only ever have a whole number of individuals in a population. It does not make sense to have 2.76 members in a population, or at least in the usual sense. So that's a big problem, because what that means is that if you were to graph this function, you would see that it has all these jump discontinuities. Ignore the red curve for a second. The blue line segments here, which resemble what we call a step function, is what the function f of t would most likely look like. That means that this function is not actually differentiable at any of those gaps, any of those jump discontinuities, which means that this whole discussion is kind of a moot point. So to get around that problem, we have techniques that we don't talk about in this class. It's actually a subject for a different class. But we have techniques for fitting a differentiable function to this non-differentiable function. There are algorithms that allow us to do this, where we can take the data that f of t gives us, this step function, if you will, and puts an approximating curve through it. So even though f of t would normally not take on any non-integer values, we can define a function that closely approximates that, for which we can do, on which we can do calculus, and that's really, really useful. So again, we're going to be thinking of f of t as a differentiable function, even though in practice it's technically not. We can get away with it by approximating it with such a function. So now that we've addressed that, dn dt, which is the derivative of that function that we talked about up there, the average, or the f of t, is going to give us the instantaneous growth rate of the population at time t. And again, if this derivative is negative, that means our population is actually decreasing, not growing. Okay, so now that we have discussed that, let's take a look at an example. This is a tricky example, so we're gonna try and tackle this using some cleverness, I guess. Well, I shouldn't say cleverness. It's just not as straightforward as a typical example. So it says the number of yeast cells in a laboratory culture increases rapidly initially, but levels off eventually. And the population is modeled by this function. N, or f of t, is equal to a over 1 plus b e to the negative 0.7 t. If you study population growth models, you'll see that this type of function shows up a lot. We call this a logistic function. You don't need to know that term here, but it is an important term in differential equations if you end up taking that class. So here t is going to be measured in hours, and at time t equals 0, we know that the population is 20 cells. That has been observed. We've also observed that at that same time, at t equals 0, the rate of growth in these cells is 12 cells per hour. So it's increasing at a rate of 12 cells per hour. We're tasked with finding the values of a and b. So these are constants, but we don't know what they are yet. We have to find them. Okay, and then there's a follow-up question. According to this model, what happens to the culture in the long run? We'll address that after answering the first question. So what's going to help here is if I write this in an alternative way, if I rewrite this function as a times 1 plus be to the negative 0.7t to the negative 1 power, because that's going to help me when I take a derivative. We want to find the values of a and b, and I don't need to take a derivative right yet. I need to work with the function as it is to start, because it says at time t equals 0, the population is equal to 20 cells. Now, if I plug a 0 into this function, the only place the t shows up is in the exponent for the exponential function here. This becomes e to the power of 0, which is equal to 1. So plugging a 0 into t here actually reduces this thing down to a over 1 plus b. So that means I have a over 1 plus b equals f of 0, which is the number of cells at that time, 20. Okay? If I multiply by that denominator, I get this. A equals 20 times 1 plus b. Now, I'm not going to distribute the 20. I'm not going to do anything like that because it's going to help me in the next step to leave a in this form. Okay? At this point, I've used this first bit of information. Population is 20 cells at t equals 0. I have not used this information yet. The population is increasing at a rate of 12 cells per hour. The rate here indicates that we're talking about the derivative of this function. So what I need now is dn dt. And that's where having the function in this form is going to be helpful. I can take the derivative of this using the chain rule. That's equal to negative a times 1 plus be to the negative 0.7t to the negative second power. So I've used my power rule there. Now I need to multiply by the derivative of this function on the inside. It's an exponential function with a linear exponent, so that negative 0.7 comes out, and I end up with something that looks like this. Negative 0.7 be to the negative 0.7t. Let's write that as a quotient, though. So I have this. This is equal to, notice that this negative and this negative will cancel each other. Everything's being multiplied here. So I'm going to get a positive out of that. A times 0.7 be to the negative 0.7t. That's my numerator. Let's write that this way. Sorry, the negative is gone, though, not negative. Positive 0.7. A be to the negative 0.7t over 1 plus be to the negative 0.7t squared. Okay? So that's what dn dt is equal to. But I'm told a value that this is equal to when t specifically equals 0. So I can plug a 0 into this derivative and set it equal to 12 and then see what that does for me. Remember, we use this notation to show that we're plugging 0 into that derivative. So this would equal, okay, and again, I'm going to be plugging 0 into the exponents, which show up here and here, turning both of these exponential functions into 1s. That's what that's going to accomplish. That's going to equal 0.7ab over 1 plus b squared. And here is where this is going to be helpful. Remember, in order to solve for two unknowns, algebraically you would need to have two equations. And that's what I'm ending up with here. So this is going to end up equaling 12, but I want to simplify it before I say that. This is equal to 0.7. A is equal to 20 times 1 plus b, and then I have another b right there, all over 1 plus b squared. Notice now I have some cancellation I could do. That's why it was useful to keep this in this form. 1 plus b, and one of those 1 plus b's can cancel. I get 20 times 0.7, which is equal to 14 times b over 1 plus b, and that is equal to 12. That's based on the information that we're given in the problem. Okay, so really now I'm just working with this part. I can multiply by that denominator. I get 14b equals 12 times 1 plus b, or 12 plus 12b. I'm solving for b, so I can subtract 12b from both sides. I get 2b equals 12, divide by 2, and I get b equals 6. okay? And if b is equal to 6, I have an expression that gives me a in terms of b. So that means a is equal to 20 times 1 plus b, which is 6. 20 times 7 is 140. These are the two values that it was asking me for. Okay, so now if I wanted to, I could go back and rewrite this function by plugging in 140 here and 6 here, which we're actually going to do to answer this second question. It says, according to this model, what happens to the culture in the long run? When it says the long run, it's talking about what happens as t approaches infinity, as time gets arbitrarily large, as time passes, and a lot of time passes. So we're going to interpret that as the limit of this function as t goes to infinity. Not the derivative, but this function. Okay, so now what I'm going to do is try and evaluate that limit. The limit as t goes to infinity of, I can plug in the values that I got for a and b here. A was equal to 140 over 1 plus b, which was equal to 6. E to the negative 0.7 t. Okay, now I know that from my limit laws, I can bring this limit into the numerator and denominator. The numerator is a constant, so the limit's not going to do anything to it. It's going to stay 140. In my denominator, I can take the limit of each term independently. Limit of as t goes to infinity of 1 will still be 1. Here, the limit of this guy is the only thing that's really going to require any amount of thinking. What happens to an exponential function with a negative exponent as t goes to infinity? Negative 0.7. As t gets very, very large, this exponent goes very far in the negative direction, which shrinks this term down to 0. We've seen that in chapter 2. So this term is going to go to 0, leaving me with 140 over 1, or just 140. What that means is that in the long run, the population will level out. I don't know why I wrote out that way. Out at 140 cells. Okay. Now I want to be careful with that because this is what we call asymptotic behavior. We know that this is a horizontal asymptote. So the actual function itself will never get us to 140. If 140 is here, we're actually looking at a function that does something like this. There's an asymptote there, and we never actually get to 140 cells if this function is accurate, but we get arbitrarily close to it. So we're just going to understand that in the background when we say levels out at 140 cells. Again, in the study of logistic functions, this number up here is what we call a carrying capacity. And what it represents is an upper bound for your population. If you take differential equations, I have a whole series of differential equations videos on my YouTube channel for when I teach that class, and we talk about this. The carrying capacity is, again, that upper bound for a population in a particular environment, and there's all sorts of reasons why that might exist. If a population of some species gets too large, they tend to exhaust their resources, and the environment can no longer sustain that population. So we tend to see something like this sort of roof for population growth in most cases. That's going to be it for section, or for not this section. We still have more to talk about, but that's going to be it for part 2.